Recorded, rolling. It's Tuesday, November 4th. So, yeah, sorry I wasn't able to be at school yesterday. I always say most of school, but I do hope you guys enjoyed that Radio Lab story and got some good out of that. Okay, and then, so we're going to pick up where we would have been leaving off from. You guys got a Kahoot, so yeah, a bunch of guys just logged on. The pin is on the board. Okay, you need that. Here, I'll do a quick review with you guys with some posters, okay, and then we'll do the Kahoot. And then we'll do a pulley lab tomorrow. So when you come in tomorrow, I have a bunch of string and weights and spring scales and stands like that. Okay, so you guys we're doing conservation of energy and energy. We're thinking about physics in an entirely different way. We're thinking about it in terms of these terms here. So if you have work that's force times distance, that means you transfer energy into some object or into some system. And so the variable is called W for work, right? Because all of these you can quantify in metric system with what unit? It starts with a J. Joules. Yeah, joules. Right. If you take newtons times meters, you get joules and so on, right? Right. So energy can take all these different forms. If you lift something, put it on the shelf, it takes work to lift it. And then once you set it on the shelf, if you take its mass, multiply by the gravity field and the height it's in, you can quantify how many joules of gravitational potential energy it has. Right? Now you do have to define where's the floor. You have to define height zero somewhere. Right. Ooh, here, let me throw a twist question at you guys. Guys, what if you define a floor? Hey, we're sitting on a second floor right now. Okay, what if I dig a hole in the floor and I define the floor that you're sitting in right now as height zero, and this falls through the hole in the floor? Could H go negative? You got negative gravitational potential energy? Could that happen?
Yeah.
Yeah, absolutely could. Okay. And then when you go to the conservation equations and you say, here, when you set up a closed system and you say the sum of the energy at one location equals sum of energy different with maybe a different time in the system. Yeah, you could still solve for say like the speed when it's crashing like the floor beneath us. You totally do that. Right? Now this universal form you don't see as often, but this is more like when there's a changing gravity field. And I do have a poster I showed you guys last week, but this simplifies to this. But when we're about this fun aspect, mostly the gold rows. If you guys just focus on these four gold rows, you're pretty good to go for the next week. Okay? Ooh, you can have energy in a spring. So, guys, does it take some force to stretch the spring? Yeah, that's Hooke's law. F equals kx. Right? Does it take more and more and more force to stretch it more and more? Yeah. Right. And so if you multiply force times distance, well, it's a changing force. Right? Put it all together, it works out that the energy stored in the spring is y dot kx squared. Remember that? So if I stretch it so much, and I know k and I know x, I can say how much work does it take to do that? Right? How much energy stored in the spring? And finally, there's energy of motion, one half times mass times the speed squared. So something's in motion, it's like a point mass, right? And then in a few months, you might eventually see this one where something's like rolling across, right? What's the energy rolling? So it's not so much of a focus now. But again, if you focus on these four gold rows, I think you're pretty much good to go. Okay, this green one though might pop up here and there a little bit. Okay, but you guys ready for? Here, let's do a little more review. A little more review. Okay. So to show you guys an example of a closed system. So as you have a block spring earth system, there's no friction, so don't worry about any friction losses. If I take a mass and I push it against the spring, and I let go, pew, it flies around the loop. Then I want to know, hey, how fast is it going at the top? So I can solve that by setting up a conservation of energy equation. I can say the energy stored in the spring, I can quantify as 1 kx squared. X is how much I spent the spring. Okay. That's like the supply of energy. Okay, well, where did all the energy go by the time it got to point B? Well, there's no friction, so there was no friction loss. Don't worry about that. Some of that went into lifting it against gravity. I'll call that mgh. Right? And then whatever's left over goes into its motion. And energy units, that's quantified as 1 half mv squared. So maybe this is, for example, like 100 joules. Maybe it took 30 joules to get to the top, and you have 70 joules left over to go into its motion. And then you can calculate the V, as long as you know the mass. Right, you guys get it? Right? So that's pretty much how it's going for last week and this week. All right, so let's switch over to Kahoot and see how you guys do. Oh, yeah, look at you guys go. I got a class of winners already. All right, work, energy, energy conservation. Got 22 questions for you guys. In physics, work is defined as well, force times distance, right? W equals FD, work equals force times distance. If you push something and multiply by the distance it acts over, right? Now, the catch with this though is it's only the force and the distance that are in the same direction. I meant to mention that during the review bit, right? Which is called a dot product, right? So if you're lifting something up some stairs, well, that diagonal, not all of that distance counts, just the vertical direction of carrying something up here, right? Some of you guys picked force times time, which is something in physics. Actually, does anybody know what that is in physics? Force times time? It's not work, but it's what we haven't even talked about yet. You see those blue banner posters on that wall? Something about momentum, something about impulse, momentum and impulse, right? So that'll come into class probably next week. We'll start talking about that. And then, okay, so you guys are good with work equals force distance. All right, got points on the board. Question two. Nellie Newton pushes with twice the force for twice the distance. Ooh, she does. Yeah, four times the work. Okay, so here, let me put this out to you guys. Okay. So if you double this force and you also double this, here, I'll throw in some numbers. What if you push with 1 Newton of force for 1 meter? Guys, 1 Newton times 1 meter. What's that? That's 1 joule. Yeah. What if you push with 2 Newtons for 2 meters? What do you get? 4 joules. Hey, that's four times the work. Okay, that's all. You're gonna just pick up some numbers and plug them in. All right, we got Nicholas, Gavin, Bruce, Kyan, Anna. The unit for work.
Yeah.
Yeah, there you go, joule. All right. Yeah, let's go over all these. It's a good review anyway. Guys, what does meters measure?
Distance.
Yeah, distance or displacement, something like that. What does newtons measure? A force. Yeah, just like how much do you push or pull? Yeah, it could be a gravitational force, right? Could be a weight, right? Weight is measured is a type of force that's measured in newtons, right? Joules measures energy or work. What does watts measure? Uh, how about power, right? Which is energy per time, right? That's like here. What 1 watt is? It's 1 joule per second. Yeah. Now you can carry energy, which we measure in joules, over let's say an electric grid. Yeah, you could plug in a light bulb or something like that, right? Um, but what watts is it's a rate of energy or rate of work, so it's joules per second. It doesn't necessarily have to involve electricity, right? I got Ella, Gavin, Kai, Bruce, Anna. Power is defined as
Oh. Yeah.
yeah, the work divided by the time interval to do the work. So work divided by time. Hey, work is measured in joules. Time is measured in seconds. So like joules per second. And that's what watts are. Okay. So here's you guys here. Right, so mostly what we're focused on is like units of energy or work. That's joules, which breaks down like this. Right? But sometimes say this type of question, like power, which is measured in watts, and power is work over time. Right? It's a rate of energy. Right? But let me show you guys something cool because when you get an electricity bill someday, okay, so this kind of does link back to electricity with this example I'm going to use anyway. Right? Normally, you're billed for how much energy you use within a certain time period, like a monthly period or something like that, and it's in kilowatt hours. Kilowatt hours. Right, you guys that? Okay. Now, I think it's weird. Like if I was coming up with a convention, I would not have done this. I would have gone with megajoules, and I'll show you guys why. Okay, guys, what does kilo stand for? What is kilo? 1,000 or something, right? 1,000. It's just a factor of 1,000. It doesn't have units. It's just 1,000 or something, right? Watts. Hey, is watts like joules per second? That's what 1 watt is, 1 joule per second. And hours. Is that a unit for time? Isn't that like 3,600 seconds? Isn't that what one hour is? 3,600 seconds? Okay. Ooh, so you could sort of get the time units to cancel, and then you would be left with joules. Do you see that? Hey, so joules is a unit of energy. I'll say E equals, right? Some number. Again, I don't know why this convention stuck. It kind of irritates me that it did, but you'll probably get billed someday for an electric bill that's in kilowatt hours, right? Uh, but more straightforward if you just step straight to the metric system. You could just go with megajoules, and it may be a slightly different number, but maybe kind of comparable. So there you go. So yeah, joules is the measure of energy, kilowatt hours, measure of energy. But watts itself, that'd be joules per second, as in work per time. There you go. I got Gavin, Kai, Bruce, Cole, Anna on fire. Ooh, way ahead. Ooh. Unit for power. Yeah, watts. Yeah, and 1 watt is 1 joule per second. Right. Newton's measures force. Meters measures distance. Yeah, watt is joules per second. That's power. I got Ella, Gavin, Kai, Bruce, Anna. The amount of potential energy possessed by an elevated object is equal to. The work done lifting it. Right? Actually, if you just look at the terminology, that's the only possible answer. Because, guys, the question is about energy. What is energy measured in? Joules. What is work measured in? Joules, because that's a transfer of energy. What is power measured in?
Watts.
Watts. Force is in newtons. Distance is in meters. Right? So even just the terminology. Right? But here, I'll remind you guys why that's definitely the answer. Because here's work and here's potential energy. Right? And if I lift something at a constant speed, I'm applying a force equal to its weight, so this force would look just like this mg, and the distance I lift it would be the height that I lift it. So this kind of is this. You guys see? It's the same thing. If I lift this and put it on the shelf, it took some work to lift it, and that's exactly how much potential energy it has. It's the same thing. Yeah, Gian, Gavin, Bruce, Kai, Anna. Kinetic energy is equal to. Yeah, 1/2 mv squared. Right. Oh, 1/2 mv squared. So that's energy of motion. Okay. You guys know this is hanging right in front of you, right? Like it's right here. Right, yes. Okay, so the answer is right there. Right. I mean, it is good to kind of know these so you can very quickly whip off equations. Okay. Right. So that when you run into a situation like this right here, you say, well, right, this is a motion. What's the energy associated with that? Oh, like this right here, just pop in. Right. Right. See all these closed equations closed system equations are just, it's just like some construction of these right here. That's all they are. Uh, yeah, Gian, Kai, Gavin, Bruce, Anna. When a car's speed triples its kinetic energy. Ooh.
Uh, you-
Increases 9 times. 9 times. Okay. So okay, let's run a numerical example. Okay. And then I know I have a here it is. Poster for this too. Here, I'll have this one ready to go. Okay. But let's do a numerical example here. So since kinetic energy is 1/2 mv squared, right, so you guys just said that. Okay. Let's come up with the car. Let's say the car's mass is 2,000 kilograms, based on like big old SUV, right, just because I think the numbers work on this. Right? Let's say the initial speed is how about 10 meters per second, right? Which is kind of cut along maybe uh, Yarra Boulevard or something. Okay, so the initial kinetic energy is have 1/2 times 2,000 kilograms times 10 meters per second being squared. I'll type a hard number to that. Ugh. Right, so 1/2 times 2,000 times 10 squared. Okay, and that would be 100,000 joules. You could also call that 100 kilojoules. Okay. Now let's get a new kinetic energy. And all I'm going to do, that same car, is just triple the speed to 30 meters per second. Okay. Then I'll square that and put it all together. So scroll up, scroll over, pop in a 30 meters per second where the 10 used to be. Okay. That gives me, 900,000 joules, also called 900 kilojoules. We got right. Yeah, you guys see that? By simply tripling the speed, I have 9 times the associated energy in its motion. That's right. Okay. Now, normally what I do is I just point to the equation and say, well, if you throw a factor of 3 on that v, that factor of 3 gets squared. You get 9 times the overall. But here, there's what it looks like with numbers. Like if you're ever not sure how proportions play out, you can just make up some numbers. I mean, I just made those on the fly. It doesn't matter what numbers make up, you still get the same proportion. All right, got Gian, Gavin, Kai, Bruce, Anna. Oh, how much further will a car traveling at 100 km/h skid compared to one going at half that speed? So if you double your speed, what happens to your braking distance? That's another way to say that.
Oh, oh, I mean, yeah. Oh, no, I'm an idiot, yeah. Oh.
All right. Yeah, you guys are pretty good. Yeah, it is 4 times smart. Right, so here's my classic open system scenario. Right, so this might be the system just the car. So this friction force is acting as an external force. Right? So the energy equation system will look like this. Right? We have some initial energy, which is all kinetic, 1/2 mv squared. Right? If we subtract off this force times distance of braking, that's the work done by the friction. You end up with zero mechanical energy at the end. Right? Right, so there's a few middle steps, but it doesn't look like this. Right? The key here, and it really links back to the last question, is that if you throw some factor on the speed, that factor gets squared in terms of its energy. So before it was you triple the speed, to get 9 times the energy. That would translate, by the way, to 9 times the braking distance. Here, I'm saying, well, what if you double the speed? Well, that would be 4 times the initial energy. So there's 4 times the energy. Well, that has to dissipate into the road. So since the work done by the friction force is very simply directly proportional to the distance, that's going to translate to 4 times the distance. Yeah, you can make up some numbers and throw them in all day, but whenever you double the speed of the car, it's always going to end up 4 times the braking distance. So it's that right there. Yeah, you guys did pretty good on that one. You guys remember that one from last week? Gian, Gavin, Kai, Bruce, Anna. An arrow and a bow has 70 joules of potential energy, maybe spring potential. How much kinetic energy will it have after it's been shot? Yeah, so all that energy would presumably go into its motion. So yeah, you can set up an equation that looks like that. Potential goes to kinetic. Right, all 70 joules, conservation of energy. Cayenne, Gavin, Kai, Bruce, Anna. As a pendulum swings back and forth.
Great.
Yeah, all those are true.
Rosie.
Quick,
right? Yeah.
Here,
Same.
let's go. Let's go through this. Okay. Uh, yeah,
I read all.
I think it was did I show you guys the Paul Hewitt where he did this with a bowling ball? Where he had a bowling ball. You guys remember this?
Yeah.
Right? And it's on a big old rope here. Okay. And then he pulled it back to right back here. And he let it go across the room. Right, then it was over here. Okay. And then we just swing back and forth. We say, if you analyze this in terms of energy conservation, then here, guys tell me, right when it's at the bottom right here, it has all what type of energy? Kinetic. Yeah, it's all kinetic. All kinetic. Okay. So that's assuming that you define height 0 to be at the lowest point, which is a common thing to do. You could say, okay, well, at that point, it's 100% kinetic. What about the endpoints? Like right here, it's all what? Yeah, potential. Okay. Um, Now here's its height relative to that floor. Call it h right there. Okay. And the bowling ball has some mass and, well, has some speed as long as it's not at the endpoint. Okay. So here, guys, suppose it has 1,000 joules of potential energy here. How much kinetic energy does it have right here? About 1,000 joules. Right? Does 1,000 joules here match 1,000 joules here? Yeah, because it's a closed system. Right? As long as there's no frictional loss, it can just swing back and forth forever. All right, Kai, Gavin, Bruce, Anna. One job is done slowly. An identical job is done more quickly, say in a lesser time period. those jobs require different amounts of. Yeah, power. Right, because yeah, okay, this one's kind of a like parsing the words. Because when you see identical job, that's to say that maybe it's lifting the same object, the same height, or something like that. It would be the same amount of work or the same amount of energy. Right. Now, if you do it more quickly, that's just over a different time interval. So, guys, if it's more quickly, is that less power or more power? If you do something more quickly, here, I'll point it out on the equations. Maybe you guys can figure it out. So, guys, right here. But you kind of get it from here. So, you guys know power is work over time, right? Okay. So, you can see it in the units. So, if you do an identical job, same number of joules, but in a small time interval, wouldn't that be more power? Here, I'll show you guys. What's 100 joules divided by, say, 5 seconds? 20 watts. Okay. Right. Now, what if you do it more quickly? Like, let's say in 2 seconds. Ooh, that's 50 watts. Ooh. Right, so that's more power to do it in a lesser time. So you can kind of figure that out. Yeah, Kyan, Kai, Bruce, Gavin, Anna.
Yeah, I beat you first.
Which requires more work, lifting 70 kilograms up 2 meters or 35 kilograms up 4 meters?
More work. Where's the bunny? Like why it's not right. I knew it. I should have trusted my gut.
Yeah, same word. Right, because right. And so
I'm Bruce.
do you guys see that
I'm
the
Bruce.
second object has half the mass of the first object? Right. Guys, if it has half the mass, does that also imply it has half the weight? As long as it's the same gravity field, that would be true. Right. Oh, but it's lifted up twice the distance. So going back to flip the screen here. Okay, here we go. Going back to here we go. This will answer it.
Some stimulation.
Okay. Either one of these. Right. How about if it's half the force but double the distance, doesn't the half and the double cancel? And it's the same amount of work. I saw this. Got Kyan, Kai, Bruce, Gavin, Anna. Object that has kinetic energy must have what? Yeah, there you go. Right. Right. So, guys, kinetic energy, that's 1/2 mv squared, right? So it has to have a mass and it has to have a speed. Acceleration is a rate change of velocity. Well, that doesn't have to be the case. You could have a constant speed. So you can have zero acceleration and still have kinetic energy. Still have a 1/2 mv squared. A force applied to maintain it, also not necessarily true. Like if you're out in deep space and there's Voyager spacecraft just kind of coasting along, it has a mass and a speed, but there's no force really on it. Right. The answer is actually one that we haven't talked about yet. So momentum is mass times velocity. Right. So that's all those blue banner posters over there. We'll get to probably starting next week, which is really a good unit to start talking about how things collide and what happens during collisions. Right. So when we get to it, it's like, oh yeah, right. It's just different ingredients to make, or sorry, it's the same ingredients to make different types of units. Right? Got Cayenne, Kai, Bruce, Gavin, Anna. Ooh, a pulley system. You guys gonna build some of these tomorrow? Yeah, so anything except the red option, right? So can it multiply the force? Yeah, that's called a mechanical advantage. So even if you're not able to lift something really heavy, well, now you can lift something heavier than you normally would be able to. Right. Okay, yeah. Multiply the force. You can also change the direction of the force by changing the direction of the rope that you're pulling with. Right. Yeah. Okay. What you cannot do is increase the amount of energy in the system or increase the work done if it's phrased that way, as a physics term. because that would be like increasing the energy, but that would violate conservation of energy. So that's one thing you're not allowed to do. Okay. And so here's one example of a of a pulley system. All right. All right. So here, let's do a little review here. Okay, suppose you have something really heavy here, like this clunk, right? And you have your spring tail on the other side. Let's play with the small force over here. You see this? Can this pull us up? See that? Okay. Ooh, but look how much I'm pulling the spring tail, and look how much the weight's moving. You guys see it? Those are different, right? Of course, it makes it kind of a silly animation, but here I have a pulley system very different over there. But that wall, you could try it. It's like the same idea, same thing. So let's put some numbers together. Guys, suppose this right here weighs 30 newtons. You guys got that? 30 newtons? 30 newtons. How much does it splits three ways? You guys see the geometry of this pulley system splits three ways? So what's the tension and the strength? What's 30 divided by 3? 10. The tension's only 10 newtons. So how much do I have to pull with over on this side with the pulling? With the spring scale? 10 newtons. 10. With 10 newtons? You can put the 30 newton weight. Can you do that? Yeah, that's what this is. Okay. But there's a catch. The catch is for every 10 centimeters I want to lift this, I have to pull how many centimeters on my side? 30 centimeters. Right? It's a 3-to-1 ratio the other way. And the guiding principle is right here. Work input is work output at best. That's if you have a 100% efficient system, like no frictional losses, nothing like that. Right? So let's see. What did I say the numbers were? So 10 times 30 equals 30 times 10. But do you guys see how energy is still conserved? Right? You're not actually creating energy. Okay. Spencer, Kai, Bruce, Gavin, Anna. How many joules of work are done on a box when a force of 25 newtons pushes it 3 meters? Oh, yeah, 75 joules. There you go. Work is force times distance, right? Um, ooh, guys, suppose there was no friction loss. Maybe you have an air hockey table. Could you guys imagine that? What if you have an air hockey puck on an air hockey table? You push it, 25 newtons for 3 meters. Right? Would all that energy on that flat air hockey table with no friction, would all that energy go into its motion? So could you set 75 joules equal to 1 half mv squared? Right? And if I gave you the mass, could you solve for the speed? Yeah, you can figure out exactly how fast that air hockey puck was moving. Yeah, you know with that? Got Spencer, Kai, Bruce, Gavin, Anna. How much power to do 40 joules of work in 5 seconds? Yeah, 8 watts. And so take 40 joules, divide by 5 seconds. That'd be 8 joules per second. It's called 8 watts. Right? So you guys know power is work over time. You just divide it. So you divide. All right, Spencer, Kai, Bruce, Gavin, Anna. How much work to lift a 30 newton crate? Lift it 2 meters. Yeah, work is force times distance. So you just take your force 30 newtons that it takes to lift it, multiply that by 2 meters, 60 joules. Yeah. So suppose you had a big old battery and that was connected to a machine that was automating this. You just hit a button, it just pulls energy out of the battery. It just pulled 60 joules worth of energy out of that battery. Yeah. Right. Of course, there's like a finite amount of chemical energy stored in that battery. Yeah. Some of it was lifting that crate. Got Kai, Spencer, Bruce, Gavin, Anna. How much power expended lifting 60 Newton crate 10 meters in 2 seconds?
Minimum. I don't know.
All right. Yeah, 300 watts. So let's see, power is work over time. Work is force times distance. So put it all together. Well, like 60 newtons times 10 meters, that'd be the work done. That's what, 600 joules? Is that 600 joules of work? Right? Divide that by the 2 second time interval. That's 300 joules per second. Also called 300 watts. Yeah. So you guys good with power? All right, got Kai, Spencer, Bruce, Gavin, Anna. Machine puts out 200 watts of power for every 1,000 watts input. What's the efficiency?
Oh, yeah.
Yeah, 20%. Right. Now, this is assuming it's a continual thing. No, yeah, machines realistically do have some efficiency like this. Like, how about your car engine? Do you think your car engine, the gasoline you might put into it, has some energy and chemical bonds, and then the mechanical energy is making the car go? Your car engine efficiency is probably fairly comparable to this. Maybe a little more efficient, but probably comparable. Right. So here's some definitions for efficiency, which actually, is part of your lab tomorrow. Where's hold on. Let me find your lab. Here's your lab page here. Because look really close to your lab page. Look at the empirical measurements and how many you got to keep track of. You got what's the input force? What's the output force, which would also be the weight? Okay. What's the input distance? How far did you have to pull the spring scale? What's the output distance? How far did you lift the weight? Okay. Now, for something like 1 to 1, hopefully these numbers kind of match each other. But for some of these other ones, maybe a little more exciting. But then I want you guys to calculate ideal mechanical advantage, which is the ratio of the distances, actual mechanical advantage, which is ratio of the forces, right? Which should be fairly close to each other, but they might not be exactly the same. And then you can calculate efficiency. So how can you do that? And there's a few ways. Okay? So straight off this page, I think the easiest way would actually be this last box. So here's, does anybody know what Greek letter this is? Oh yeah, I did remove that poster, didn't I? Oops. So eta, it's Greek letter eta. And a lot of times in physics, it's used to represent efficiency, just like here. So you could just take the ratio of actual compared to ideal mechanical advantage. Right? Now, there's some other perspectives too. So you could do useful work out compared to total work in. And this could be like your the gasoline example with the car. So you put in so much gasoline in your car engine that could sort of represent this denominator. And then something about moving the car around, like getting the car up to speed on the highway. That's like this numerator, basically. And then just divide the two. Yeah, you do that, right? And then for say like heat engines or engines in general, a lot of times this middle formula is used, right? One minus waste heat over total work in, which matches really nice to this picture right here, right? So you put so many joules of work in, you get some useful work out, like making a cargo or something, right? Then there's some waste heat that you inevitably lose, right? So next semester, we'll also talk about laws of thermodynamics and a concept called entropy, and this will almost certainly come back to. There you go. There's a preview of all that. Also help you on your lab tomorrow. All right, got Cole, Spencer, Bruce, Gavin, Anna. A sled starts at rest top of a 13-meter tall snow-covered hill. What is the maximum speed of the sled at the bottom of the hill? Assume Earth gravity. That's a reasonable assumption. Earth gravity. Ooh. Yeah, so 16 meters per second. Right. Yeah, it turns out it doesn't actually depend on the slope of the incline or anything like that. Now, if you chose that, maybe it'd be understandable why that might be intuitive, but it actually doesn't. So, guys, whether you have a hill that does something like this or a hill that does something more like this, okay, let's suppose both of those are the same height. They're both 13 meters. Okay, so I got h equals 13 meters here. I got h equals 13 meters here. So it's the same height hill, but one's very steep and one's less steep. Like I said, I put a sled at the top and let both of these slide down. Right. Let me ask you guys a different question. Guys, which one does the sled reach the bottom faster? The first one or the second one? Yeah, first one. Yeah, this one will reach the bottom first, and this one will lag behind. Right? But it turns out that as long as there's no frictional loss, they have exactly the same speed at the bottom. And the energy equation goes like this. Sum of energy at the top equals sum of energy at the bottom. Okay. Guys, what form of energy at the top? Potential energy. There's your MGH. And if you define the bottom of the hill as height 0, then where'd all the energy go? Kinetic. 1/2 mv squared. Right? Now, the math cancels. So, I didn't even give you a math of the sled, but it cancels anyway. Or if you have a light sled versus a heavy sled, makes no difference. Okay. And we're solving for this b. Ooh, guys, I see 2 algebra steps. Can I cross multiply this 2 right here? So I got a 2GH, 2GH. Okay. And then that's V squared. So how do I get V? I have to take the square root. Hey! That's the same answer as the Galileo question. Remember, Galileo just dropped the ball straight off a vertical tower. Right, just straight down. Right? Yeah, vertical drop. So let's start up here. I'll do the rest of the math over here. Kind of running out of room there. So I'm getting speed. There's really the maximum speed. Like if there's no first law. Square root 2gh. So let's go square root. Guys, what's a reasonable gravity value for Earth?
Done.
Yeah, let's call it 10 meters per second squared. Even if you go 9.8, it'll land it pretty close. Okay, and then go 13 meters. So I'll throw that all in the calculator. See what happens. Square root 2, 10, 13. I'm getting 16.1. I'll just call it 16 meters per second. Let's see what happens if I plug in 9.8. Very curious. 9.8. Ooh, 15.96, which also rounds to 16. So yeah, there you go. That is it. All right, you guys good on that? On that? All right, for the win. You guys ready for the win? For the win. For the win. We got Kyan, Spencer, Bruce, Gavin, Anna. Ooh. A tall snowy hill is 3 times taller than a short snowy hill. So 3 times taller. One slider starts from rest at the top of the tall hill. One slider starts from rest at the top of the short hill. The 2 sliders slide down. There's negligible friction. What's the ratio of the speeds at the bottom of the hills? Remember, one hill is 3 times as tall as the other. I bet you could use the same setup we just did.
I don't know.
Well, you got 30 seconds.
I can see it.
Here, guys, I'll switch my screen just for a few seconds here. Guys, it's the same thing as this, except make a hill 3 times as tall. Is it going to be some version of this? What if your hill is 3 times as tall? Right, so the G's the same. The H is just a factor of 3. What happens to the V? Right?
Nice. Oh, nobody recognizes this thing, but
yeah, that's the square root of 3. 1.73. This is the square root of 3. Right here. Before I go to the winner podium, I'll show you guys exactly why. Right. So I guess so. V would be the speed at the bottom of the hill. Right? Has nothing to do with how much is the hill incline. Nothing to do with that. Right? There's no frictional loss. Right? All that matters is that comparing the 2 hills is they have a height ratio of 3 to 1. Right? So if you slip in a 3 here, it's underneath the square root. Watch this. Square root 3 is 1.73. That's the square root of 3. 1.73. Okay? And if you're still not quite sure, let's do this. I'll have speed at bottom of tall hill. I'll do speed at bottom of short hill. Okay, I'll set up square root 2gh on each of these. So 2, let's stick to 10 meters per second squared because we've been using that. 2, 10 meters per second squared. Okay. Now I need a hill height. And okay, I got a random number generator right here. We're about to figure out how tall let's start with the short hill. The short hill is 58 meters. Ooh, well, not so short, but let's go with it. 58 meters. And let's see what is 3 times that. What's 3 times 58 meters? Is 174 meters. You guys see that? 3 times 58. Whoops. There it is. 3 times 58. You guys remember get these numbers, right? This one I got off the random ball. And then I just said 3 times that to get the tall hill. Right? Now let's see what are these speeds. Square root 2 GH. I'm getting 58.99. Here, I'll just call it 59 meters per second. The short hill, let's plug in a 58. I'm getting 34 meters per second. So the speed compared to the speed. Now if I divide those two, 59 over 34 meters per second, meters per second. I bet you I get 1.73. You guys think I'm going to get 1.73? Let's see. Oh, yeah. 1.7. Okay, these numbers round a little bit, so pretty much 1.73. Okay. And that's a ratio. Okay, so you're going 1.7 times faster from the tall hill compared to the short hill. Okay. Now, you can make up any hill height. You'll still get that ratio as long as the hill heights are 3 to 1 ratio. Okay. All right, let's find out who won. Kahoot. With the bronze, Bruce. The silver, Gavin. And the gold, Anna. All right, nice job, guys. Nice job. All right, let's see. Since we have a few minutes left,
Yeah.
let me remind you guys what's going on with the lab tomorrow. Right, so let's do a couple minutes here. Right, and then when you guys come in tomorrow, you'll have some spring scales like here. You'll have a box of lab weights like these. You'll have some string. You'll have some of these pulleys, like these spread pulleys. Right. There's some double pulleys. Right, you guys see this double pulley? I don't know if I put these out so much so far, but these two individual pulleys can rotate individually of each other. So if you wind one string around like clockwise, the other one counterclockwise, it can go separate directions. So sometimes that's nice, especially for the fancier pulley setups. Okay? You'll have some kind of bar or some kind of system that hangs from. Okay? So you'll have all those items. Right. And I'm going to have you guys bring up some different pulley systems. So I'll see if you guys can do this all within one class period. Is to rig up a pulley system with a 1-to-1, 2-to-1, 3-to-1, and 4-to-1 mechanical advantage like this. Now, can you see what would give you mechanical advantage from each one? Or like if I just gave you a picture, would you know which mechanical advantage is which? Okay. So a good trick is to look at what's a fixed pulley versus a movable pulley. You guys remember that animation I played last week? I know it was a few days back, but they were rigging up different pulley systems. They actually showed these three on their animation. Here, guys, let's look at this one right here. This pulley right here. See this pulley right here? Is this fixed in place, or does it move? This one's fixed in place, right? But not this one. You see this? Like as you pull this spring scale, see this one's actually going to move up and down with the weight. You see it? That's called a movable pulley. And I do have a pulley system rigged up over there by that wall. So if you want to play around with that, you can kind of see, like some of those pulleys are fixed in place and some will actually move up and down. You see that too, right? Now, if you focus on the movable pulley, you can very quickly get an idea of what your mechanical advantage is going to be. Because whatever weight this is this weight's being split. How many ways? 2. You see it? So wouldn't that give you a 2-1 mechanical advantage? It's kind of like the weight's been cut in half, sort of, right? Because what about this one? How many ways is the weight getting split? 3 ways. Yeah. Like this weighs 30 newtons. Looks like 10, 10, and 10. So now the tension of the string is only a third of the original weight. Yeah. Do you guys think you can figure out how to wind the string around tomorrow to make that? Actually, this one has a bigger picture. Oof. There's a big version of it that's hanging up in my room over there. So you can kind of just model that one. And then a 4-to-1. Can you guys make a 4-to-1? Now, this one, it might be helpful to actually use the double pulley. And instead of these 2 individual single pulley, which you can do too, you can just link 2 of them right on top of each other. There's nothing wrong with that. Okay. But it might be more convenient to put them side by side. It's this double pulley right here. Okay. Do you guys see 1, 2, 3, 4 strings going up? You guys see it? Yeah. So it's kind of like the weight's effectively getting split 4 ways. So if this weighs, say, 100 newtons, I bet you only have to pull like 25 newtons to lift it. Yeah, like that. Okay, and then, well, here. Right. Last few things here. Right. So when you're looking at ideal mechanical advantage, that's the ratio of the distances moved, which is pretty much just the geometry of whatever you're building. Right. But actual mechanical advantage, take the ratio of the forces. So you might not get the full mechanical advantage if you look at the actual. Like, for example, maybe the ideal here is like 3-to-1, but maybe the actual, when you divide the forces out, might be something more like 2.5-to-1 or 2.8-to-1, something a little less than 3. Right? And then that takes you to that efficiency. Oh, where's my efficiency poster? Oh, it's right here. If you take the ratios of mechanical advantages, that's probably the fastest way to calculate this efficiency right here. Right? You might get something like 80%, 90%, something like that. Okay. You might get 100% if the mechanical advantage will match. That'll be a 1-to-1 ratio. It's called 100%. All right, so that will be tomorrow's adventure right there.